the main thread in an activity. Yes. So there's two ways of doing that. Either you can use an alarm service.
Okay, so today we will discuss a little bit about the threading, about how to do concurrent programming in Java and on Android. And also we will focus on how to do background work on Android and how to interact with the UI. So I gave you a simple task to generate a default application which will have the hello world running. So I can start it, and it's the default empty app which starts and have a main activity with a single view, which is the hello world label. And I ask you to write a small modification which will run a background thread and change the label to hello from thread. So how can you do that? How can you start a new thread in Java? Yeah? New thread? Yes, that's right. So what we can do is here, yeah, the fonts. Bit bigger, yes. I should be bringing a mouse to those sessions, so you can do the fonts by scrolling the mouse.
Can't you do this by holding Control and then?
No, because you don't have a wheel. I can't. Where are the fonts? Color and fonts.
Editor again. Oh yeah, appearance, fonts. Yeah.
Yeah. What was that? 20?
Oh, probably get away with that. Yeah? See.
Visible enough? Bigger? 22? About that? All right. So I need to grab the label. So if I say, well, first of all, I need to have a handle to the text view. So let's say text view, and then I will have this TV equals find view by ID, R ID, and we have to have a look how it's called. Main activity has a text view which doesn't have an ID, so we have to add an ID to it. Android ID, we call it TV hello. All right, so we have that sorted. We go back to our code, and we can get this TV hello. So now one suggestion was I can start a new thread by saying new thread, and then I have to implement a method and then run the thread. And inside the thread I have to have a public void run method, which I implement my modifications. So I would say TV set text hello from a thread. All right. Can I compile it and run it? Let's try. So let's stop what's running there. Let's compile it and run it. So Gradle is building. It finished building. It's bootstrapping. And it's working. Interesting, right? Why I'm kind of puzzled that it's working. Why it kind of should not really work. Well, so Chris?
No, let me do it. I saw some hands.
Can't run UI things on threads.
Exactly. So normally I should not be able to modify UI from a non-UI thread. I have one UI thread which is allowed to modify the UI, but here we're modifying the UI from a separate thread which should not.
No, you don't.
Huh?
No, you don't.
Yeah.
Anyone sees anything?
Well, I did a mistake. Yeah, I see it now as well. So there is a simple coding mistake. I'm actually not running a new thread yet. Any hints about this run thing? Yeah? Exactly. So starts a new thread and then runs the method run inside that thread. What I did, I basically created new object which has type thread, which has a method run, and I run the run method on that object, which without creating a new thread, right? Okay, very good. Thanks, Chris. So let's redo it. Let's stop it and let's run it again. And this time, what do we expect? Yeah, we expect a crash. Okay.
Not helpful.
Why are you not collaborating?
Is the label set to hello world? The default label?
Yes, it is.
No cat, anything?
Maybe you need to override the function run.
No.
Yeah, so that's the hello world here.
Okay, what am I missing?
What are we missing here? Well, we do, but the override is simply enforcer of the annotations. It doesn't really change. Yeah, let's quickly redo it. It will not. Yeah, so it restarted. It still prints hello from a thread.
Can you wait on this, sleep on this, perhaps to see?
Um,
Updating UI. Which API are you running?
the latest, I think.
That shouldn't work.
So we're running.
Android.
Yeah. Min 21, 26 is the compiling one. All right, anyway, the point of that exercise is supposed to be that you're not supposed to modify the UI thread from a background thread because you have to do it from the UI, yeah?
Can you do it via runnable? If you have provide runnable implementation to a thread, does it make a difference?
We can try that. So Chris suggests that instead of overwriting a new thread, we basically do something else. So this code works. It starts a background thread. We can sort of, yeah, let's just, before we do that, let's do a sleep. So we will see hello world. So let's sleep for milliseconds. So let's sleep for a second, or like 2 seconds. 2 seconds sleep. Yeah, because I have to wrap it with the, whoops, surround with the interrupted in case while we're sleeping there is an interrupt coming, we have to handle that. So we just print the stack trace on. So let's restart that. So hello world, and after 2 seconds, crash.
Yes. Yeah.
Excellent. That's what we want. So why it worked without the sleep? Well, I don't know. Maybe there is some optimization going on, and the UI thread realized that, okay, we can quickly run that extra thing in the main thread or something. I don't know. It's a little bit surprising. It's not supposed to work.
No.
It's supposed to crash, right? So we cannot do that this way. What Chris suggested is, so I will comment that. I will show you another way of running a thread. So what's a different way of running a thread using the thread class? So what was the called?
New runnable. You just not on thread. It's directly new runnable.
But how you start it? You have to schedule it. So runnable has to be run.
You create a runnable and then
pass it as a constructor. Okay, yeah.
Yeah, exactly.
So you can create a new thread,
yeah.
And then the thread. Yeah, if we browse the. Oh, oops. If we browse the docs, yeah, we will update later. It has a constructor. I cannot make it bigger, but let's see. Preferences, fonts. Yeah, let's do it on the browser. So if I go to a browser, Java thread API. So from Java 7, if we check the constructor, we will see that there is a version of the constructor which takes the runnable instance, right? And it allocates a new thread with the runnable instance. We can do that instead of what we did by overriding the method. We will also start it. So we'll start the thread here. And instead of overwriting the thread class, what we will do is we will specify new runnable. And then the runnable has a run method, and we basically do the same thing inside the runnable, right? So I can do this instead, and it will be exactly the same piece of code, correct? So I can rerun it, and where is my... Where is the... Yeah, hello world, and after 2 seconds crash, right? Exactly same behavior. Great. A little bit of syntax. This is a single interface with a single method. So if we look up runnable, so if I go again to... Oh yeah, that was a good... if I go here, I see this interface with a single method called run. It's in the new language, it's called functional interface, because it's an interface for a single function, right? Because it's a single function interface or functional interface, I can simplify the syntax to get rid of some of the boilerplate. So I can delete that, and I can do Lambda expression, and I can delete all that. Work. So, oops. And I just need to delete this as well. And I have now a Lambda expression. Oh, not yet. Now I have a Lambda expression between those two braces as a body of the method, and this is a parameter list which that method takes. So it's a function which doesn't have a name, which takes no parameters and has this body, right? So catch is missing. So catch, I must have deleted interrupted exception. So let's do nothing.
This vector is still one line up.
Yeah, that's true. So this one needs to be here. Right. And it was called IE Great. And now Lambda expressions are not supported in this language level, right? Can we use Lambda in Android? No.
Oh, but which API did they conform?
Let me check.
Then, okay.
Yeah, so Chris will check it, but in normal Java, from Java 8, you can use this notation. So if we can use Java 8, I think we can. I would have to change the project settings.
Yeah.
Project SDK.
Java 7 by default.
Can you switch to Java 8?
With some helper tools.
Okay. All right, so we are stuck with
There are some plugins, but
with Java 7, so we cannot use this feature. But if you're programming in Java 8 onwards, you can use Lambda expressions to substitute some of your code with this. So let's not do that. For this piece of code, what else can we do? So how else can I start a new thread? Yeah? You can use AsyncTask, exactly. And for this particular task, AsyncTask is the way to do it, right? So we would have to start, specify a new AsyncTask. And we would have to specify what it returns as a, what it takes and returns as a parameters, and override onPostExecute method. And in onPostExecute method, we would update the UI, because the onPostExecute method is actually executed not in the background thread, but in the UI thread, right? So AsyncTask is the solution to this problem. But what if you really want to do something like this? If you are having some background thread which works in the background, how can I now update the label from my background thread? Yeah?
You use run on UI thread function.
Correct. So there are a couple of methods. One method is suggested now, using the activity run on UI thread. I have to, so our main activity, this run on UI thread, right? So there is a method which allows you to pass the runnable into this call, and this runnable will run in the UI thread as well, right? So I can do this, and I can say new runnable, and it generates this stuff for me. So I will move my code here, right? So now what we do is we do the sleep in the thread. So we do some background task. This sleep basically emulates doing some work, right? So we're doing some work in the background thread, and then when we are done, we need to update the UI, and we're using the run on UI thread, passing it runnable, and it will run this runnable in the UI thread. Let's test it. So let me refactor the code a little bit before we test it. So I will take this piece of code. So I will delete that, and I will move it to another private method, void do some work. Okay. So I will put it here, and align it. We can format the code later. do some work. So it kind of emulates that we're doing some work by waiting 2 seconds. Okay, so now the code is a little bit clearer to follow. Well, no, I did do some work in the wrong place. We're doing some work here. Okay, so we're doing some work, and after we've done some work, we need to update the UI, and we can do it this way. So let's test it. So it starts, it says hello world, and after 2 seconds it says hello from a thread. Great, right? So no crashes, it correctly updates the UI. What's another way of updating the UI from a background thread? So that's one way. In the main activity or in the activity class, there is a method called run on UI thread. What's the other way? Another way was to use AsyncTask, which was also good. But if we have a kind of a long-running piece of work, we should not use AsyncTasks. And we will talk a little bit about it in a moment, but I just want to finish this thread of discussion. So one possibility is to use, let's say one possibility is to use the main thread run on UI thread. What are the other ways of achieving the same thing? Yeah. You could use broadcast receiver. Yes. That's a little bit heavier to demo. So let's say broadcast receiver. So what we would need to do is we would initiate like a broadcast, and from our main activity would register a callback as a broadcast receiver. And when from the background thread you kind of notify the thread, notify the Android OS that there is a broadcast, then the broadcast receiver would be triggered, and then in the main thread you can update the UI because the broadcast receiver will run in the main thread, right? Yeah? Yeah. You could. That would be another one. That's another really heavy one. So let's move it. So let's say this is number 3. Number 4 would be to use a background service for result. So we would run something, and then once it finishes, the result would be passed back, and then on result, callback would be called again in the main thread. Both of those are quite heavy, right? We can use them, but they are quite heavy. This one has a huge advantage of not needing the main thread or the main front-end application to actually continue to run when we doing the background work. So this one is quite special, okay? So the special thing about it is that when I start the activity, I have the front activity running, and let's say we have a background service which does some background work. Normally, for the other methods, with the exception of this one, so this is kind of an exceptional method, the front-end activity has to continue to run for the other methods to work. If the front-end activity is killed by the user, then the background thread will be kind of killed with it, and it will never be able to call back to the front-end activity because it's gone, right? So that, you know, TV, the variable here is like, it doesn't exist anymore because it's been killed. It has been garbage collected. There is no main activity anymore. But with this method, I'm notifying the broadcast receiver, and then the OS will decide, okay, there is a broadcast which happens, and you can show the user some sort of notification of some sort. and then the user can click on it and invoke a new instance of the main activity, right? So this, with combination with the notifications, allows you notifications allows you to have a long-lasting background task with no front-end app at all running in the background, and then when time comes, notification comes, and through the notification you can kind of invoke the front-end app to do something, right? If you're just using a broadcast receiver, I think that it will not start automatically, right? If it's not running. You need the notifications for that. You need the user action to launch the actual front-end app. So on its own, broadcast receiver will not do that. So on its own, broadcast receiver will be the same as the other methods. But if you if you use notifications, then you can sort of start something in the background, and then the user can kill the front-end app, but the background thing will continue to run until it finishes, and then it will notify the user. User can click and bring up the new instance of the activity, and then you can update the UI.
The reason you shouldn't run anything long-lasting a broadcast receiver, like starting an activity or something like this, is too long. May take too long.
Yeah.
So you may get an ANR.
So let's say number 4 is notifications. And then number 5 was the service for result. And what's number 2? What's the other easy way of doing that without the this method on activity? Because I sort of need to have a handle to the main activity to call this method. Well, so the number 2 is if we bring the browser and if we go to, how can we navigate? Yeah, let's do all classes. Let's go to view. View. Oh, Jesus. Yeah, I should do the reverse search. So I should go this way. It will be faster. Zone view. Yay. So if I go to view, and if we check the view class, well, view post method. Android API. So if you, where is the API? No, come on. Android view post API reference post. All right. So we have a kind of a family of methods on the view, which are prefixed with post. So let me just show you again. So the very basic one is called post, and it takes a runnable action, right? And what it says it causes the runnable to be added to the message queue. What is this all about? Well, in Android you have the UI thread. Okay, so imagine that you started your app, and the UI thread starts, and then the UI thread, loads the resources, generates the window, populates the window, and so on. So it executes the code. What happens if it reaches the end of whatever it needs to do? What happens then? So you have a thread which starts running. It does what it needs to do. It loads, the window, loads the label, prints hello world, and then what will happen to the UI thread? It would end, right? So it cannot end, because then it would sort of stop, right? Once the thread finishes at the closing bracket, it just gets killed, it gets garbage corrected. So it has to go into some sort of loop. So those of you who are doing game programming, they know that we always have a game loop, right? So in the game loop, we process the user input and we update the UI for the user in a game. So we do it, 90 times per second or something, depending on the refresh rate. We sort of render the game in a loop. So we check what the user is doing, and then we process the user input and we update the UI. It's exactly the same here. So the UI thread is basically a loop. And inside that loop, it has kind of like a looper which manages the messages which all the UI elements tell the looper that some small work needs to be done. So when the user presses a button, there is kind of an event which the button says to the looper, saying, look, I was pressed, you have to animate me being pressed. And this piece of work gets into a queue, and when the message queue is being processed, that animation is being played when the user is pressing the button. It happens, instantaneously, but it still happens through managing a loop and managing a queue of events which a user is generating or we are generating. So we can add something to this queue, and then when the looper is going through, the handler is going through the all the messages, our things will be executed at the end, right? So when we do this, we can attach a little bit of code which will be executed after the loop goes through all the current things in the queue and before it goes back to start from the beginning of the queue again, right? So if the queue is empty, the loop will wait for things to be processed, and then if the queue is empty, our thing will be the first one to be processed, right? We can do a little bit more. We can, for example, call post delayed. So we can update the UI with a bit of a delay that we need, right? So we can say, I want this to be done in the UI thread in 10 seconds, right? Or in 2 seconds, right? So some of the Microsoft progress bars you think are done this way, right? So they say, okay, in 2 seconds, move the progress bar to certain thing. It's completely unrelated to how long certain things take. So you can use those two methods to pass the runnable and update the UI by this method, right? So what we can do here is, instead of doing this, what we could do is we can say post and then new runnable and basically do the same thing, right? Oops. So now our version 1 and version 2 are kind of equivalent. So you can use the post on any of your UI elements to force something to be added to the UI thread message queue and then be executed, at some point. So we can comment this and do the second version instead. So if I relaunch it and go here, we were late, or it's still doing? Maybe we were late. Let's relaunch it again. Yeah, let's just kill it and run it from the beginning, because something is not quite right. So hello world, 2 seconds, hello from thread, perfect. So those are two lightweight methods of updating the thread from the background thread, updating the UI thread from the background thread. The other three methods are also possible, but they are heavier. They require more resources to do that. There is one extra thing that I wanted to talk about, this kind of threading here. So one way of starting new thread is this. The other one was to pass the runnable inside. But we can also do a little bit better, especially if we have to manage multiple threads. So what we can do is we can call executor new. We have a kind of a utility class in Java to help us manage thread pools. So we can create a pool of threads and sort of schedule tasks on those threads, right? So for example, here we have a fixed thread pool, which takes how many threads do we need. And we can say we will be doing some jobs on 8 threads or 4 threads. We have, let's say, 8 core machine. So we would like to have a multiples of 8, maybe 16. So we will say we will have a thread pool of 16 worker threads, and we'll be scheduling some tasks on those threads. So we can create sort of a pool of 16 threads using one of those utility methods. We can have a single thread scheduled for us. So we can use this call to just create a single thread, so a pool of single thread for us. And then we can have some sort of scheduled thread pool, which will have some size, but then we'll have a factory of how the threads are being generated and given to us. So if we use the simple one, so let's say we have 2 threads. So we'll say executor service. And then instead of saying new thread, what we will do is we would say es what's the code? It's not run. Yeah, I would need to look it up. Schedule. I thought it's schedule. So executor service API. So in executor service we have execute. So execute, and we pass runnable. You see? So it's very similar to the thread API, which takes a runnable inside the constructor. We can say execute, and then we will pass new runnable, and then we overwrite the we override the run method, and of course we need the braces. I cannot type standing. I have to sit. Right, so it's runnable and go all the way to here, and then we don't call start because it will, you know, execute that in the pool automatically. So we will say execute. Okay, so let's rerun this. So it's restarting. Hello world, 2 seconds, and hello from a thread. Perfect. So this is a kind of a cleaner way of doing it. Why? Well, the reason is that with the executor service, you have control over your pool. You have control over your threads. In the previous case, we created an instance of new thread. Remember, we did this. New thread, and we didn't even have a kind of a handle to it, right? And there is limited stuff you can do with a thread. You can't really do much once the thread is running. Yeah, you have a reference, but you know you cannot really properly stop it or manage it and so on. With the executor service, you can kind of force certain things. You can force certain things on the threads that you're running, and you can. So currently we're running a single thread, but we can execute, with executor service, we can execute multiple jobs to run on those threads. And they will be kind of run, you know, if I execute something before this one, and I said I have 2 threads, those 2 things will run concurrently. But what will happen if I execute the third thing? Well, it will wait until one of those 2 finishes, and then it will be scheduled on the pool, right? If I want to run 3 things concurrently, I have to increase my pool to 3. So it gives you flexibility, and it gives you kind of a way of managing the resources that you have, right? Does it make sense? So let's do a small experiment. Okay, before we do the small experiment, as Chris was saying earlier, why shouldn't we run async task for tasks that take long time? What do you think? So async tasks are perfect. I mean, they allow us to update the UI once the background work is done. They are quite easy. You put the do in background part in the method for doing in background, and then on post execute for updating the UI. It's a single instance. You know, they are quite convenient. But if you need to fetch something from the URL, if you need to fetch your RSS feeds, or if you need to do something which takes substantial amount of time, why is using async tasks not advisable? Yeah?
You don't know if the activity that called it will be alive when this is done.
Exactly, exactly. Imagine that you started an async task for fetching like I have the app for lab 4 for browsing my RSS feeds, right? And in the background, you've started the fetch, right? While you're doing the fetch, a user turns the phone into landscape mode. What happens then? What happens normally when I turn my app from portrait to landscape? The normal behavior is the activity is killed and it's restarted with the landscape mode again. So it can redraw everything from scratch, right? So if you don't override the default behavior, what will happen is your original main activity will be killed. Your new main activity will be started with the landscape mode. And while you're doing your background task, the background task is kind of hanging now because it's attached to the old activity which has been killed. And then, you know, the moment you go to the to updating the UI of the old activity which doesn't exist anymore, you will have a crash, right? The app will crash on the user. Yeah.
Isn't it so? It's if you
kill the main activity,
Yeah.
then async tasks are not somehow killed.
No, they're not killed.
In cascade.
No, exactly. They continue to run in the background until they try to execute on post execute, and then this call, as soon as it touches anything in the UI of the activity that doesn't exist anymore, will throw an exception. Yeah.
But then async tasks like fetching the RSS don't need to go directly to UI.
Exactly. So if you have a task, async task, which doesn't touch the UI, the situation is even worse, because what will happen is the app will not crash. Oh yeah, it's maybe not worse, but it's different. So the app will not crash, but it will lead to a memory leak, because every async task is attached to an activity which started it. So even though you've turned your phone around, the old activity is still kept in memory because the async task references it and will be never garbage collected. So as long as the async task is updating something or doing something, you actually have to keep it in memory, right? So every time the user does this and you're trying to do something in the background, it kind of will have some hanging orphaned object trees, which will be kind of not garbage collected, because the garbage collector would have marked the original activity to be garbage collected, but because the async task is referencing it, it will not, and because it will not garbage collected, the async task is also referenced from the activity, so you have a circular dependency, and those two objects will kind of never be garbage collected, strangely.
Even if the async task is done.
Even if async task is done, exactly. So your app will eventually crash because of a memory leak, right? So you're not supposed to run long-lasting tasks like fetching URLs from a web in the async task. What you should do is you should do something like this. You should run something in the background and then update the UI when it's done, because something like this will kill the threads which we've just started, because we have the proper reference to the executor service in your main activity. So if your main activity is garbage collected, all those things will be kind of wiped and it will be clean. Sometimes you want to run something in the background for a long time, and usually it's good not to do these things here in the main activity. It's good to do those things from the service, right? So this code technically should be moved into a service. And the UI and main activity should be just kept for the UI aspects, right? Right, so any questions about that? So when would you use async tasks? Well, you would use async tasks everywhere where the chance of user turning the phone into landscape mode is minimal. So if something takes really short time, or if you're actually updating the UI. So you have, for example, a list view, and you've been doing some processing, and now you need to update the UI, right? If the processing is not immediate, like you have to rescale, like, I don't know, you have to rescale some icons, you have to format some text, and you want to display the list view kind of nicely, you would do this preparation work in a background thread, and then the actual update of the UI in the on post execute using the async task. That's perfectly reasonable way to do it. Because it sort of relates to the UI and it's kind of a short. But for anything related to network, you probably should not use async task. For things related to disk, if it's really fast, that's okay. But with network, probably not.
But if you do it in a service?
Yeah, so in the service you can do anything long lasting, yeah.
So in the service, in an async task?
Yeah, but then if you're doing it in the service, why would you use async task? Why wouldn't you use executor service instead? Async task kind of carries extra things, and also to run async task you have to have a UI thread, because you cannot start async task from the background service which doesn't have a UI thread. So you would use this, right? Is it clear? Is it clearer than it used to be? So it's kind of complicated, yeah?
But what is the user does turn the phone?
Yeah.
Doing something that's supposed to
So if the user turns the phone and you've already launched the async task, as I said, if the async task finishes and calls on pause execute, the app will crash. You're screwed, yeah.
Can't you safeguard?
No. So with the latest APIs, we've observed some weird behavior with async tasks, right? So with the latest APIs, maybe they safeguarding it, right? So I haven't tested it. Definitely with the older APIs, your app will crash. With the latest ones, because they're doing something a little bit weird, maybe the app will not crash, and maybe the memory leak is also addressed, right? But I don't know. And also you don't know which API will your users run your code on, right? With the older APIs, it will crash, and there is nothing you can do about it. So the way to deal with it is to kind of use something like this. Okay, so let's complicate it a little bit more, and let's have an integer which we will call counter. With all those threading examples, it's kind of contrived, but it's the simplest way of demonstrating sort of a point. And we will initially have it set to 0. So let's say it's set to 0. Let's have a final static counter max being 10. And let's have how many threads? Let's have 10, a pool of 10 threads, and instead of doing this, so I will delete all of that for now. Right, so we will have a loop. We will loop from 0 to 10, and we will start 10 threads which will do some work. So all of them will do some work, and then they will increment the counter, right? So I will say counter plus plus. And then once it's all done, it would be nice if we also have, so, okay, so what this code will do? Can someone explain to me what this code will do?
For each loop, you will try to get them thread from the pool and do some more, and after it's done, call the counter. So probably if it will, if it takes a long time, so it will go to the next loop and start a new thread. So probably we'll start all 10 at once.
Yeah.
Because it's faster than some more.
Yeah.
To the next iteration.
That's right. So it will start 10 threads, and those 10 threads will wait for 2 seconds, right? Concurrently, and then they will increment the counter by 1. So what should we get at the end?
Depends if they are synchronized.
Yeah, the code is what it is. So I will execute additional thing. So I will have a new runnable. So apart from running those 10 work threads, I will have an additional thread, right? So I will check if counter is bigger or equals to counter max, and if it is, I will say TV post new runnable, and we will say TV set text work done, counter is plus counter. Okay. And I in fact, if I do that and the counter is not max, I will quit my thread. So what I really want to do is I want to check while counter is less than counter max, I will do what? I will kind of busy wait. So I will say thread sleep, 50 milliseconds and then retry. And once I quit this loop, I will do this. We don't need that. Okay. So I have to remove the semicolon from here. Good point. Everything is fine. I will kill the previous app and I will code. What's the shortcut? Auto indent. Nice, nicely formatted. Okay, so I'm running 10 threads, and yeah, let's do a small modification of that because so let's do while counter is less than counter max. Stupid brackets. Okay, so okay, and let's reduce the waiting to 1 second. So the work will take 1 second. And the threads do this. Let's just run one, okay? So I'm running one worker thread. The worker thread will do some work, increment the counter, and then loop back to check if the counter is still less than counter max. If the counter is equal to counter max, I will quit my loop, right? So now when I run it, how long I have to wait for the work done to be printed? I just have one thread. I mean, I have two threads. I have one which is the worker thread and one which is kind of waiting for the work to be done. So it says hello world. And now, how long should I wait for the threads to finish? 10 seconds, right? Great. So did we wait 10 seconds? Yeah, I guess. Let's run it again. So 101, 102, 103, 104, 105, 106, 107, 108, 109. Right. roughly 10 seconds, okay? What will happen if I say now I want 10 threads to do that job? How long should I wait now for the job of incrementing the counter? Theoretically 1 second, okay? So let's rerun it. Yeah, it was pretty fast, right? It was about 1 second. What's wrong with this code? Why this code is unsafe? So let's make the counter go to 100. And let's redo that again. Again, it should take about a second, but now we're counting from 1 to 100. No, it should take 10 seconds because we only have 10 threads doing the job of incrementing the counter to 100, right? So on average, it will take us. So let's increment that to 100, and let's increment the pool to 100, and now it should take us a second, right? Yep, around a second. Let's run it again. And let's run it again. It's a little bit cumbersome, but if I were to redo this experiment multiple times, is it possible for me to see here 101? Why?
Race condition to update the counter.
Exactly. So this line of code is thread unsafe. I have to read the value of a counter, and then I have to update it by 1, and then save it, right? So my threads may see. So one thing is that because yeah, let's say I have 8 threads and I have 8 core machine, right? Chances are, if I do this, then those 8 threads will kind of run on each core, right? The core, they kind of grouped, so they have kind of a L1 cache specific for the core itself, and then L2 cache is usually shared between a pair or 2, and then L3 and the RAM are sort of general, right? So if the value of the counter is stored in RAM and the core needs to read it, it will see the global value. But if the core already prefetched it into the L1 or L2 cache, it will reuse the one from the cache, right? And because the threads kind of run concurrently, they may have inconsistency of what they see between the L1 or L2 caches versus what's in the RAM, right? And this kind of code doesn't enforce the synchronization with the main RAM, right? The keyword to fix that is volatile, right? So I can prefix this counter by saying it's actually volatile, and that tells the compiler that every time we're doing something with the value, it should be read from RAM and passed to RAM, because then we're guaranteeing that the different cores will see the same value, okay? So it fixes one of the problems. So if I run it now, it should take a little bit longer because the cores have to do read and writes from RAM instead of using the caches, right? So if you have some more heavy computations and you do that, the computation will take a little bit more time, but it will be safer. This doesn't fix the race condition though. So the race condition here is because this line of code really is something like this. I'm saying there is a value v, which is the current counter, right? Then I'm saying v equals v plus 1. And there is another line of code which says the counter equals v. Okay, and while I'm doing this logic, another thread might have already read the counter and might have already updated it by 1 and increment it, and here I will be kind of overwriting the value which has been already done. So instead of running something for 100 times, I might be running something for 101 or 110 times, right? So I can, so if the value is 1 when I read it, and then I've modified it to 2, and then I'm overwriting 2, another thread might have done it already on value 1. So I will twice write 2 to the counter, right? So if we were to count how many times we've done the work, it may turn out that we've done the work more than 100 times, right? Because we've probably have some of the threads have the race condition and overwrite the value more than once because of this situation, right? So what's the solution to this? So what if I only want to run the logic 100 times, not 110 times? Well, the simplest way is you write a method. So you say, I have a method, it can be private, that increments the counter, and it does the increment for you. So it says counter plus plus. And this method is synchronized, right? And now, instead of you doing this logic, you say, you say inc. Right? So that's the simplest solution to the problem. So now we are guaranteed that whoever is updating the counter has an exclusive lock on the variable, and no other threads will be able to do that, right? So when one thread calls inc, another thread which calls inc will be stopped because one thread is already calling inc. And it will be waiting until that thread finishes, and then it will kind of go. So if they're like, you know, in our case, 100 threads running concurrently and trying to call inc, only one of them will get the lock, will do this call and quit, and the moment it quits, another one which was waiting will execute. Yeah.
So this inc is happening after do some work. So if
yeah.
there are multiple threads that are reading counter being 99,
yeah.
and they are starting the work, and then they will anyway run this. Yeah, I mean this while condition is also should be somehow synchronized because when the one thread is already doing some work, then the counter is not updated yet. So all the other counters threads can get the old invalid value of counter anyway.
Very, very good point. So Tomasz' point is that even though we cannot override the value of the counter, we can still run something even though the counter has been already incremented, right? Yeah.
Could you put synchronized on the override run function? So it's an override.
No, well, but that doesn't help us. Like this runs in a thread. It's one thread running one method. No other thread is touching it, right? So this runs in one thread, another thread, and even if you say synchronize, nobody else is calling it. It's only one object calling it. Whereas this is a single reference, like our main activity is a single object, which multiple threads call, and then synchronization makes sense, right? And no, you cannot put synchronized here. It would make no sense. Yeah, so Tomasz' point is that when we checked, so we checking here and we're saying the counter is 99, so I have to do some work, right? There is no really way around it in a sense, yeah?
Could you, this increment function, could you make it return a bool and then somehow put it, the code inside a while in the condition?
Yes, exactly. You can do that. So we can rewrite it in such a way that it returns an int, and we can say,
because you increment while you're checking, and then somehow locking the global counter.
if inc is less than counter max, we do the work, right? So this way, we will only do the work if it happens that we are less than 100. Yeah, that's a better way of doing that. Okay, what's another solution for? Yeah, we have to return the. Return the current value of the counter. Yeah, what's the? Yeah. So what's another way of doing that? Yeah. Use kind of a lock.
I think there is like a monitor in Java that can just check your code for like the race condition. So it's quite automatic. I haven't used it myself.
Okay. So I haven't used it. But let's say we basically have to prevent multiple threads touching that thing, or when they do touch it, they do it atomically, right? So there are kind of another two ways that you can do that. One is to have a lock, and before you do your logic, you will check whether you can obtain the lock. So let's delete this, and let's have and there are kind of multiple different locks you can use. So one is just reentrant lock. It's a very basic one. And then there is a read-write lock, which is a little bit more advanced because it allows you to have multiple people reading, right? When you're writing, you don't need to have a lock. No, when you're reading, you don't care if somebody else is reading. If nobody is writing, everybody can read, right? So if I have 100 threads which only read, then they can read at the same time. But if one thread is writing, nobody should be able to read, because then you have race conditions. So that once the writing happens, everybody is forbidden to be reading. And once the write finishes, then again, everybody is allowed to read, right? So if you have kind of an imbalance between reading and writing, the read-write log is better because it allows you to distinguish when you need to read only and when you need to write. And then it's more performance-wise, it's beneficial. In our case, we're doing reading and writing at the same time. So in our case, the reentrant lock is the one that we need to use because we have no benefit of using the read locks or write locks. So we'll have kind of a lock. And we can say we have, a lock variable. And here, yeah, we don't have that anymore. So we have to use the counter. And before we use the counter, we have to obtain the lock. So we will say lock yeah, what was the, I think it's called lock.
Yeah, just lock. Or try lock if you want to avoid deadlock.
Yeah, so yeah. Can we get into a deadlock here? can we get into a situation where two threads are trying to, are kind of are busy waiting for a lock, and one already obtained it? Well, we could if we are uncareful about releasing the lock, right? But if we are careful, then this will work. So I will say, you know, obtain the lock, and then try. And then we will do finally, and we will say lock, unlock, right? If we do that, we sort of guaranteed that you cannot have deadlock, because no matter what happens, we will always unlock the lock, right? And if we cannot obtain it, we will kind of wait here. So if somebody else is using the counter, we will wait. When somebody else releases the lock, we will do our logic, and then we will unlock the lock. The problem with this code is that the first thread which catches the lock will do all the work, right? It will not allow other threads to do it, because this loop will loop until it's done, and then it will unlock the lock, right? So yeah, and we have to increment the counter at some point. So let's say we do the counter like that. So how we need to modify it? Well, we have to modify it by saying, well, we will only lock for updating the counter, but we don't have to lock for the while loop, right? So we have to kind of turn it around by saying we will do that. So let's say while counter is less than counter max, we will no, we will not lock. We will do some work. And then just before we need to update the counter, we will lock. And then we update the counter, and then we unlock. That code has the same problem as our initial thing, that we will be doing work even at 99. So we checking the counter. The counter is 99. We're doing the work, and while we're doing the work, somebody else might be doing the work as well. And then it will get to 100, and then we get to here, and we will get to 101, right? Because we will be updating the counter after the counter has been already updated. So the way around it is to sort of do similar thing as we did, that we do the check, we do the we do this bit of code before we get into the while loop, right? And we check if we are at 100, right? You get the idea? Do I need to write it? So we do this first, and then we check if we still under, and then we do the work, right? So we lock, and then if the counter is already, we can do, let me write it. So we will lock. We'll obtain the lock, and then we have to check if counter is less than counter max. Because if it's already 100, we are not gonna increment the counter, right? And we will check. We will set also some sort of a bool here. So yeah, so we're trying, if the counter is less than max, we incrementing it, and we unlocking the lock, and then we have to have
do you need the while lock then?
Say it again?
Do you need the while lock then, or just run do some work?
No, so I will, yeah, so let me just finish this. So I will have a Boolean flag. Should I do work, which is false. And then this one will say, should I do work to true? And then I would say, if should I do work, then do work. And then we have to wrap it. Okay, and the whole thing will be wrapped into the check, but the check, so yeah, we will say while counter is less than counter max, do check if we can get the lock. So lock, update the counter. If it's, we have to do it again, because while we've been locking it, somebody else must have already get to 100, right? So even though while may say, okay, it's 99, you should do the work. If we get here, it can be already 100, and then we will not do it, right? So only if we still under the counter, we're doing that. We unlocking the work. We checking if we should be doing the work, and we doing the work. What I'm missing? Yes, I'm missing that, and no semicolon here. So this is for the while, this is for the run. I need another one for the runnable, and I need this one for this one. Okay. It's a little bit more complex, right? And I have to do this second if inside after I have obtained the lock to make sure that, you know, while I was obtaining the lock, you know, the other thread didn't update the counter here. And then I will loop. While I'm doing the work, the other guys can obtain the lock and they can check, right? So all the other guys will kind of obtain the lock and potentially start doing a work with 100, with like, if I'm doing the work for 97, somebody else can be already doing work for 98 and doing work for 99 and so on, right? But the moment I am doing work for 100, if I updated it to 100 and said, okay, I'm the last one doing the work, I will still do the work, but the next guy who reads the counter will have the 100, so it will quit the loop, right?
Could you still use the synchronized around objects?
You can, yes. So you could use synchronized for obtaining the lock on the object before you update it, right? So instead of so Chris' idea is, instead of doing the lock here, which is the kind of the reentrant lock, what you can do is you can synchronize on the counter itself and do that piece of code being synchronized on the object. So I can rewrite it. So instead of locking here, what I can do is I can rewrite it by getting rid of the try and finally. So I get rid of this, and what I say is synchronize on the counter. Synchronized on the counter and do that. Yeah, I could do that if I turn the counter into the integer. For this piece of code to work, right? So for this piece of code to work, this has to be an object. Currently, it's a primitive type int. So if I kind of turn it into the integer, it will work. And with the counter plus plus, it will box and unbox, right? So this is the same as before. I just don't have to deal with some of the verbosity of the lock. The lock happens automatically for me here. So whoever calls this line will lock on this object, and somebody else, another thread calling this line, if somebody already obtained the lock, will wait until the one of the locks is released. Yeah?
Won't that one call lock twice, one for plusing and one for checking?
This one will call lock only once here, inside this, between those two brackets.
Oh, okay.
Here, for this code, right?
So then why do you have to specify counter?
Because I have to lock on something.
But you lock that whole sequence.
I lock this sequence, the blue sequence, on this object.
But there are two instances sort of that counter.
No, it's only one. It's only this one.
Yeah. Yeah. How to explain that? Yeah. Okay.
So here I didn't got the lock. I'm unsafely reading the counter, right? It can be 99 or it can be 100 already, right? I don't know. So I'm like, if it's 100, I quit the while. I'm done. If it's 99, there is a chance I will be the last one doing the work, or I will not do the work. So then I lock on it. And then when I lock on it, then I have a guarantee that I'm the only one having a lock. So while I'm reading it here, nobody else can update it anymore. So here it can be 99 or 100. If it's 100, I'm done. I'm not doing the work. But if it's 99, I will set it to 100. Only I will set it to 100, and I will do the work, and then I do the work. So in this block, only one thread will be updating the counter at the time. Yeah?
The line with the should I do the work, so shouldn't it be inside if? Because then it's...
Which line?
And the line...
Yeah,
line,
here. Yes, you're right. There is a... Of course it should. It's a typical bug, which is because you don't use braces for your if statements, right? So, you should be orthodox and do your braces even for one-liners, because otherwise you may end up with those bugs. It was a bug, yes. Very good spotting. So I have to do this line inside the if statement. Yeah. Good. So there is one more way of doing it, and it's called atomic. So you have a couple of atomic, things, like atomic integer, for example. And if we say our counter is an atomic integer, then you will, we have to say new atomic integer of 0 initial value. And then I actually don't need to synchronize on it anymore. The code would still work with synchronizing on it. But what we really want is we want to do, yeah, so let's, so what we're solving is we're solving the problem of read and write at the same time. So here we are doing the work. Yeah, so here we will say, so we have a couple of methods. So one of the methods is increment and get, right? And only one thread at a time can be yeah, so yeah. So the idea here is that we can set a value to yeah, how we would use it. So the idea about atomics is that you have an ability to read the value and then modify it in kind of a transaction. So if you need to do two operations, which we have to do, we have to read the value and then increment it, right? And those are two operations. Then we can have a race condition because one thread can do one thing at the time, and that's what we discussed before. And atomic allows you to sort of do these two things at the same time, atomically, right? So we don't really need to compare. We would have to say, yeah. So we could use this. The problem with this one is at the 100, we will still, like at 99, if this is 99, and two threads are kind of at that position, two threads may be able to kind of do the same thing, and then we end up with yes, that's right. So we would end up with 101, right? We cannot go over 101 because if you've done it once, then you're done. But we can end up, because we have 100 threads, we can get quite above 100, right? So that's not ideal. Yeah, let's check. Let's check if we can do.
Isn't it like here you actually need to compare between get and increment? Exactly,
because we need to have a comparison, but the comparison only had a value, not kind of a range. So let's see if I can compare it. Yeah, you see, so I can compare, but it's like equality comparison. It's not like less than comparison. What we really need is if the value is less than something, then we update it based on the current value, right? So it's a little bit more complicated to what the atomic integer allows us to do. Yeah. Well, so it kind of yeah, if we do that, let me just delete this. Right, so when we ran it previously, we had always 100 at the end of the run. It was saying, okay, the counter is always 100, even though because of race conditions, more than one thread was doing the job. So we had more than 100 of do some work done, right? If we do this way, the counter will provide us the actual value of how many tasks we've done, right? So I need, yeah, I deleted the es execute new runnable, yes, while counter is less, I have to say counter get value is less than counter max. I will thread sleep for 50 milliseconds, and once I'm done, I will say TV set text jobs done. We had do some work, run for counter get. Right, so if I do this now, I expect the number to be more than 100. We're doing the pool of 8 threads. Was it? 8 threads. We adding and we counter maxes. Yeah, good. So our app crashed. Why our app crashed? What did I do wrong? Where is the bug? Anybody? I'm not running the update in the UI thread. Now I am. So we solved one problem, 196, right? We did almost double the job because of the end condition, because all the tasks wait for about a second. They kind of all almost at the same time read the counter, which says it's 99, and like 96 of them read the counter 99. So they've done the work again and, you know, incremented correctly the counter, right? So we've solved one problem. We have kind of a correct value now for how many times we've done the job. We know for sure that we've done the do work 196 times, but if we were to prevent the last one to do the work, we have to do a little bit of gymnastics with the atomic to be able to achieve that, right? You know, given the API which we have for the atomic, I don't think you can actually do that without resolving to something else. Within the atomic, we cannot check and set using the less than. We can only do that based on the equality check, right? Can we do that with 100? Can we? Yeah, let me see how the compare works.
It's only one thread that is calling this method, so probably it would work.
No, all threads are calling that method at the same time. That's the problem.
So it's not like that the method call is not atomic?
The method call, the call is, yeah, the call is atomic. Yes, you're right. So the call is atomic. So we can do that.
So nobody else will call it, and we will get the results before the other is solved. So if you compare and increment, then the next call will return 100. If it's 10 threads waiting for at 99
but
counter.
Well, our problem is we have to read the value, check it if it's still not 100, and then increment it. If it's 100, we're not supposed to do anything, but the check is based on the inequality, not on equality, right? So let's say, so currently 2 threads calling this method, and the counter, let's say, is 99. Both of those 2 calls get executed, right? So the yeah, you're right. So this bit is not done because this check is 100 for one of them. Yes, you're right. So it actually works. So even though the counter says 196, only the ones which returned 99 will do this part, and the other ones will return 100 and 101 and 102. They will increment the counter, but they will not do the job. Yeah, good.
You could probably even do something, make some kind of the internal counter, how many times the job was done.
Yep.
Instead of,
yep.
Just putting
sure.
Inside this while loop.
Yep. We can do that. So let's add volatile int job counter, and the job counter initially is 0. Again, we have the let's use atomic integer, right? And inside do job. So when the do job actually does the job, it increments the counter. So what we will do here is job counter at or increment and get. We don't care about the value actually. We just incrementing it. So in a sense, yes, that's what we need to do, because we need to.
How many times you get inside the while loop?
Yeah, that's right. So we say job done plus job counter. Job counter plus by attempts, and then we print how many attempted to do that, right?
I think it's enough if the job counter is just volatile and not necessarily atomic. Because volatile fixes the issue with adding and you trying to add to the same value at once, whilst the other atomic value.
Good question.
I'm quite sure that it's enough because
so so the question is, do we really need to have the atomic integer here, or is volatile already solving our problem of 2 jobs incrementing the counter?
Because they are just incrementing it 100 times now, because we have it inside the do job, and that only executes when the other atomic value is actually incremented correctly.
Yeah. So volatile solve us a problem of reads. It doesn't really solve us the problem of writes.
I think it does read and write, but it doesn't for.
Yeah, it does. It does for writes as well. Yes,
yeah,
that's right.
It doesn't solve the problem if you do it like read once here and then write once lower down, like at a different point in time.
Yeah, exactly. Yes, exactly. So so the alternative here is we do counter plus plus. right? And the question is counter plus plus correct, or is it possible for it to lower our value? So if I called do some work from 100 threads, they call this method, is it possible with this option to have a counter being overwritten? So one of the threads got the value.
That one has to be job counter.
Yeah. Job.
We still have threads doing some work parallel.
Yeah, so this increment is not safe.
Yes, no.
No.
But the do some work only happens 100 times.
Yes, but they can do. You can have multiple threads running it at the same time.
Yes.
And then we'll have a.
If it's volatile, then it should correctly update. Like if to run it at the same time, then both will iterate at once.
Yeah, but it doesn't happen at the same time. So as I was saying, like this job plus plus is effectively int v equals job counter v plus plus.
Not if it's volatile.
Wait, and job counter equals v. So job counter is volatile, right? Which means everybody who reads it will see a consistent value.
Yeah.
So one thread reading it will see value 100 or 99, and another thread reading it will see the same value. If I delete the volatile, it is possible that at that line, two threads reading it at the same time will see different value.
Okay.
Right? That's what volatile solves. Volatile doesn't enforces atomicity, it enforces the same view over a memory location. So without volatile, I can get V if two threads are doing that line now. If two threads are executing that line, one can say 99 and one can say 98. If I set volatile, I'm guaranteeing that this line will give me for all the threads the same value, 98 or 99, right? And then this happens. This may happen in one thread faster than in the other thread. And then this happens, right? When this happens, the write will go straight into the memory, right? So the next time somebody reads the value, will see the correct value. But two threads already read this value, and I can overwrite it. So two threads can read 98 and say 99 later. Does it make sense? Let's do that. Let's have another job counter. So I will have another volatile int job counter 2, which is also 0. And this guys will also increment this guy. Job counter 2 and job counter 2 equals this. And to be, yeah. So let's, and I have to print it. So jobs done plus in brackets, we will put job counter 2. Ten seconds. Jobs done. Atomic value says 100. Volatile says 99. And the total attempts were 194 this time. So the edge condition was a little bit less, But you see, volatile didn't solve our problem. The two threads still read the correct value and had a race condition to override the value at the same time. So they both incremented it to 99 or whatever the value was and overrode the thing, right? So if we change the volatile to not volatile, it will get even worse, right? So volatile solves a little bit in our favor, the odds of the race condition to be a little bit less, but it doesn't solve the problem. So this still produces, you know, a race condition.
So mostly the reason you use volatile, that is for semantics and for making it easily visible for other programmers.
Consistent visible, exactly, yes. So you're making it volatile, so you have a kind of a consistent semantics across threads. They see the same thing, right? And you're also notifying the programmers that this is a shared variable, but it doesn't solve the atomicity for you. It just reads, like, you know, without the volatile, as I was saying, different threads can have a different caches. They can optimize it, and you can have a total chaos, right? One thread here at the same time can tell you 1, and the other one can tell you 10. It's possible, right?
But making it both volatile and atomic, that was like other than visibility for the programmers, that doesn't change anything, right?
I don't think you need to make it volatile if it's already atomic.
You could just remove this volatile signature and run it again.
For the atomic, I think it will make no difference, I think.
But it's still better to have it.
It's better to have it, yes. Again, 10 seconds. Well, now we have 93 for the volatile job counter 2. So we had more things. For this atomic, yeah, we can't verify it. Which we were, yeah, the job counter, yeah, this one. So for 100, it's still 100, right? It didn't change anything. It's still correct. So for the normal job counter, it worked fine. And I think it will work fine because it's not a atomic thing. It's not like a primitive type. For primitive types, I would always use volatile. But for atomic objects, I think they are by default volatile. Like the runtime system enforces the writes because it has to maintain atomicity of them, right? So just specifying that it's a volatile doesn't really add it. It is by default volatile, I would say. With C++, this gets much more complicated because you have more flexibility and ability to express the semantics that you need. So you can say, I want the read semantics to be consistent. So when the threads read, I want to ensure that it's consistent, right? Or you may want to have kind of a consistency on writes, that when I'm doing writes from two threads, then it goes to RAM. So it's all about the performance. If you say volatile in Java, it kind of makes reads and writes go through RAM, which means it's kind of slower, as I was saying. In C++, you can kind of control where your trade-offs are, how much you can have a flexible semantics without sacrificing the logic of the program, but to benefit from the performance of what the runtime system will be doing, what the cores will be doing with the caches, right? So it's sort of, it depends what strategy, what mechanisms of synchronizing between the caches and the RAM you want. Here you'd have no options but either turn it on completely or turn it off. With atomic types, it's turned on by default, and with primitive types, you have to say volatile. All right, so that was quite a quick run through synchronization, through locks. The reentrant locks or the read-write locks, through executing pools of threads and managing the threads, and how to do a UI. Using the post is quite convenient. Yeah, my IDE is like turning the the runnable into the Lambda expression in the IDE, you see. So normally it's just I type the new runnable, but the IDE is actually turning it into the Lambda expression in both cases. But we couldn't use the Lambda expression.
I think you can by modifying Gradle file. You can set up the source version and the build version for
Java 8?
Yeah, for Java 8, and then it should work.
Okay. I always pick the wrong one. So do you have
compile options in compile options block, that one on there.
Okay. Let's try that. So I will change compiler or compile options. No, it doesn't give me compile options. Yes, great. So compile options, source compatibility. I have to say Java version, and you pick 1.8 and target compatibility Java version. You can even pick, according to my ID, I can pick up to 10. So if we do that, and we sync the project, and if I go to my code, and if I really use the Lambda, so let's see if I can do that. So, crap. So we need to delete all the way to here, and then I will do Lambda expression and the Lambda expression goes all the way to here. Okay. I'm missing a closing bracket for the execute. Oh no. While this less brackets basically. So this is for this is for this is here, this closes that, and semicolon after the round brace. No, it's a block. You don't use semicolons after the block. Yeah, it's fine. Why this one complains? Yeah, so now it says, oh, look, anonymous inner class runnable can be replaced with Lambda. So replace with Lambda. And do some work is never used. Well, why? We're calling it here. Yeah, so replace with Lambda. Cannot resolve. Do some work. Do some work.
So, closing brackets, are they all?
Import. We're not using AsyncTask. Yeah, but I don't need to clean that. What else do I have wrong with the braces? Oh yeah, here we have this is the end of the lambda. That should be fine. Oh yeah, I have another lambda here, right? Yes. So I'm missing, yes, so it's a little bit of a hell with the curly braces now. I need to have this body of this lambda inside the curly braces with this closure. Yeah. Now what this complains? Another curly brace, why? I have that one. Oh yeah. Set. Okay. Yeah, code, auto indent. I am missing the closing of yes, of this method. Yeah. All right, so I fixed all the brackets problems. In fact, you can, if it's only a single expression, you can get rid of the body brackets. So you can kind of have it like this. But I will put the curly braces there. Right, so let's run it again, just to make sure that everything is fine. Any questions about that? So the takeaway from this is, for your lab 4, when you're fetching the some resources from the network, do them in the service and do them in the service in the background threads. Communicate from your service via some of those mechanisms that we discussed to your UI, to update the UI. One of the really convenient ways to decouple your UI from your background work completely and basically use like a database for doing the checks. So here we managed to get 100. We were lucky. The unsafe job count 2 gave us the correct result. Let's see again. So if you're fetching something, so start something in the background, fetch it, populate the database. Yeah, we got 93 this time. So the unsafe one is clearly unsafe. Put it into the database, and then in the UI have a background thread which kind of periodically checks whether to update the UI. You can do that, you know, once a second or something. When you've started something in the background, right? So you can expect something to be updated after a bit, right? If you're not doing anything in the background, then don't, you know, keep updating the UI every second because there is nothing to update. This way, your UI can be sort of closed up, and the background thing can just communicate with the database. So you can kind of decouple it, but it depends what you're doing. For lab 4, you can tie it up. So when the user kills the front-end app, the background services, you don't care. You can kill it as well. So the service can run in this, you know, attached to the main activity, right? So you have a service running in the background, but it's kind of intimately attached to the activity, in which case when the user puts the activity in the background, the service might get put into the background as well by the OS. So that's one way of dealing with that. Okay, questions? Is it clearer now? Or more complicated, yeah?
Just one simple question.
Yep.
So the Java documentation mentions that semaphores are usually used for saying how many threads you have.
Yeah. Mm-hmm.
If you are using executors, like
Yep.
is there any reason why we would use semaphores?
So it depends exactly what the purpose of synchronization is, right? You can have kind of a counted semaphores, so you may have some sort of a synchronization that you want, but with the executor service, you have facilities to help you with that. So for example, if we were to wait for all the threads to finish, we have some API facilities to do that. And then you don't have to work with semaphores manually, right? So typically, I discourage people working with locks manually and with semaphores manually. Use the higher level APIs, right? There are two really good ones, which are futures. So a future is kind of like a wrapper class which allows you to have a value which doesn't really have a value yet, which is called calculated in another thread, but you can, when you really need that value, you can say get, and at that point your thread will block, right? Obviously you don't want to be doing that in the UI thread. You never want to block your UI thread, but you know, if you have some worker threads and you need to have some synchronization, you can use futures because that really allows you to coordinate without dealing with locks and without dealing with semaphores yourself. You can kind of do that on a higher level. So for some use cases, a future is a really kind of nice way of solving a problem. So in your case, for example, you have what you can do is you can have a background for lab 4. A background thread, you start a background thread which will, or future task, which will go on and fetch resources from the network. And it will prepare a future for you, which is your list of new documents, right? And then when you start this, you start another background thread, something like we've done here, where you will basically, instead of busy waiting, you will say the future get. And this future get here will block and will wait until the other task is done. When the other task is done, this future will be fulfilled, and then you will do the UI update the way I'm doing it here, right? So that's kind of a pattern, for example, for Tomek, because you had kind of the database update and the fetch done in separate threads, separate async tasks. So instead, use normal threads using the executor and have the final one, which is updating the UI, to say get and wait for the other ones to finish, right? So with the future, you can synchronize nicely the tasks that need to be done in sequence, right? And they will kind of, this thread will wait until the future is fulfilled. You get the idea? So no semaphores, no atomic things, nothing fancy, just kind of a high level, you know, a future construct, which allows you to synchronize nicely between concurrent threads.
Okay, break. Afterwards, re-amplifies the marking.
Okay, break. Sorry, I went over time. Nobody reminded me. It's your fault.
Exactly.
It's always someone's fault.